Hi everybody, welcome to the Dryden Pool Academy. I'm Flo, Sales and Marketing Manager here at Dryden Aqua, and today it's already session 15. And for this session, I'm pleased to do it for the first time with my friend Jimmy.
Hello everybody, good morning, good afternoon, good evening. My name's Jimmy Lamb and I'm Sales Manager for Dryden Aqua Pools.
And guess what, today we'll speak again about AFM, but AFM in commercial pools.
Specifically for commercial public pools.
It was requested by many of our customers. Why to use AFM in commercial pools, what results you will get. And we will cover very important topics today and also controlled in commercial pools. Number one is the pathogens. Number two are the trichloramines and the THMs, so these toxic volatile byproducts that are controlled in pools, and THMs more and more, I would say.
Mm-hmm. Total combined chlorine, so we'll break that down in what you're actually measuring with your DPD number 3.
Yeah, number 4 is the water consumption and especially this backwash efficiency of different media. We tested many different media. What results you will get with AFM compared to sand and other glass media.
And the water savings that you can expect.
The water savings, exactly, yep. Yeah. And the last point is about our new grains DIN Grade. So this is coming from the German market, actually, you know, this DIN norm. So we made a grade to meet the requirements of the German norm, and we realized that they had some advantages compared to our traditional grade 1. So we wanted to talk about it today, see how and when to use it, in which cases you should use it. So this is the agenda. So let's jump first about how it started.
Just a reminder, yeah, how it all began. So Dr. Howard Dryden, the founder of the business, marine biologist, really wanted to understand why it was that marine mammals, such as dolphins kept in captivity, had a much shorter life expectancy to those living in the wild.
Yeah.
Researched PhD in sand and zeolite filtration, figuring this would be the solution, but it was during the course of these studies he learned that he could actually manipulate the surface of glass. And this is how AFM was born.
Yeah, Dryden Howard is leading really over 40 years now in water treatment. And it started in aquaculture with it was called Dryden Aquaculture.
Dryden Aquaculture,
first,
yeah.
And it started very small, let's say, and now we have today two...
Where are we today, yes.
Ultra sophisticated, how do you say?
Sophisticated AFM factories.
AFM factories. Yeah. One in Scotland, one in Switzerland, with an annual capacity of 50 tons.
50,000 tons?
50,000 tons of filter media per year, which is starting to be quite many pallets of filter media.
Moving a lot of glass.
We are very proud of our manufacturing process. This is really unique in the world. Not only we're using 100% recycled glass that we sourced locally, but to run the factory, we use 100% solar energy and rainwater. So we produce ourselves, you see here in the video, on the roof, the panels, the facades of the factory are equipped with solar panels.
Totally covered with solar panels, yeah.
And we produce up to 1.2 gigawatt. That's 1.2 million of kilowatt hour of solar energy produced on site every year. So this is how we run the factory.
And we even run our cars on this electricity as well.
And we also plug in our Tesla cars. We have now eight chargers and more with Scotland. Rainwater, so we store the rainwater on site. We have 1,000 cubic meters of water stored on site. But not only we use it to wash the glass, but we reuse it in a closed loop filtration. So we reuse this rainwater to wash more glass and to make it as sustainable as possible.
Filtered with AFM, of course.
Zero waste. All the waste we get from the process is separated, reused or sold to other industries. For example, the sludge that we get, we sell it to biogas companies to make green electricity. So everything, we want this zero waste manufacturing process. The lifetime of AFM is also many times longer than any other filter media.
We'll show some examples.
And we can use the AFM can be reused to produce new AFM.
New AFM.
So this is really this circular economy we're looking at. Today we are present in 3 industries.
So starting in the agriculture industry, of course, Howard's background. We're making small and better gains in water treatment market, where there's a huge opportunity for our media. But by far our biggest market is still in swimming pools. About 3/4 of our turnover, I think, is in the pool market.
Yeah, if you take the total turnover, but yeah.
And breweries as well, that's one of my favorite applications.
Cooling towers, pre-treatment before desalination. You see here aquaculture, and of course our pools with over 1 million pools. Yeah.
And we have a new slogan there, Flo.
Clean water for all. This is really because we provide the best, cleanest water for not only humans, but also these animals you see on the screen, these penguins and little shrimps and so on. Good. Subject number 1, it's this biology. This is our heritage from the Dr. Howard Dryden. This is really this biological approach to water treatment that we were the first one to really come with this approach to the pool market.
Yeah, approaching pool water from a biological perspective. So, really what happens in a swimming pool, it's not a sterile environment. There's always a bacteria present, and this is why we need to add an oxidizer, usually in the form of chlorine, to keep that bacteria at bay. But what that bacteria is striving to do is to reach a surface, stick to that surface. It will then excrete an alginate around itself to protect itself from that chlorinous environment.
That's what you see on the screen.
Yeah. And we know that chlorine, even at very, very high levels, will not 100% remove the formation of this biofilm.
It's consumed from the outside to the inside to reach, and it is completely consumed before reaching the bacteria usually. So you need really high concentration, and even if you have high concentrations, you don't fully remove this biofilm.
Chlorine of a level of 50 ppm, let's say, will remove 99% of a biofilm. But that 1% that's remaining, the bacteria that's growing in there will grow resilience to the chlorine, and we start to get super bacteria growing within the system. A little bit like the antibiotic effect. If you don't take the full course of antibiotics when you've got an infection, that infection can grow an immunity to the antibiotics. So it's a similar phenomenon.
So very, very difficult to control on this biofilm in a pool system. And where do you find this biofilm?
Well, it will be on any surface that the water's in contact with. So it could be the pool tank itself. That represents, from the visual eye, quite a large surface area. And of course, we need to brush the wall and the floor of the pool to keep that clean. Then there's the pipe work, of course, a little bit more difficult to reach and clean those areas. Balance tanks. But did you know the filter media alone, if it's been sized correctly, this will represent well over 90% of the total surface area that pool water is in contact with. Every grain of sand has got a developed surface area, and when you multiply that up, that
1 cubic is about 3,000
square meters. So, and this is where all of the debris is being trapped, we hope, in the filter. So it's the perfect breeding ground for bacteria just within the filter media itself.
So you got it. 90% of where you will find biofilm is inside your filter in the filter media. This is a picture with a microscope. You can see here the sand completely covered with biofilm.
Bacteria, And this is typically what happens in a sand filter, and the reason why we need to change it, I think the advice in the UK is every 5 to 10 years.
Yeah, that's about the same in the rest of Europe.
In the rest of Europe, because you get this coagulation of the grains of sand within the filter itself. It starts to clump together, or anoxic zones as we call them. And as the water's trying to force its way through the media, it will just push these mud balls or clumps to one side, and the bed will open up, and you start to get channeling going on. So the debris that we're trying to trap will then start to pass through the filter.
And that's when your filtration is no longer
performance will deteriorate quite quickly, and then occasionally we get a rupture of these anoxic zones, and it releases bacteria flock back into the pool, destroys the chlorine, and the pool can turn cloudy very, very quickly. Exactly. And the pool has to be closed and treated to get the clarity back in time.
And chlorine consumption will increase, and this is when you have to replace your sand,
Exactly, those of you that have been and had the pleasure of going out and doing media change, you might relate to that picture there. It's particularly when you get down to the bottom of the filter around the laterals, it can be quite an unpleasant experience. I do like the use of PPE gear though in this picture, Flo.
So very hard. It stinks. It smells very bad. If you had the pleasure to do it. And if you don't have this biofilm, there is no clumping. the grain will not stick together, you will not have this channeling problem, and you get stable performance.
Consistent and reliable filtration performance, yeah.
Number 2 problem of biofilm is really a home for growing pathogens. So we talked about these bacteria that stick on the surface, start to secrete. Usually they are the Pseudomonas.
Pseudomonas, these are the pioneers of building, the building blocks, if you like, of a biofilm, yeah.
And then inside this biofilm, they will welcome other species, kinds of bacteria. You have here the amoeba, which is a very severe, dangerous one, that live in the biofilm, and also that get feed from the Legionella. And so they eat the Legionella until they explode.
Yes.
And you have these pathogen peaks.
This is really important, because if the amoeba is allowed to consume the Legionella and it's safe inside the amoeba now, and once it multiplies and bursts from an amoeba, if it's then released into the water column, and that water isn't treated properly, particularly in spas or hydrotherapy pools where there's agitation or aeration of the water, that Legionella can then be released into the fine droplets that you breathe them in as a bather, and it goes into your lungs and enters the bloodstream that way. That's what it can cause
Legionella is very severe. When you inhale them, when you have blowers in spa, jacuzzi, very careful. You get the Legionellose. This is the name in English?
Legionnaire's disease.
Okay.
Do you know, if you drank a glass of water with Legionella in, absolutely fine. The acidity of your stomach will be able to deal with that. But it's when we breathe it in.
And the more food, the more organics, the more bathers in the pool, the higher the temperature. That's why I mentioned the spas also. The higher this growth rate. And you see here the mature biofilm on the right side. The pointer is
down at the bottom.
Then you release this flux of bacteria back into, and if you have this channeling, then that's when you get your problems.
So eliminating the substrate for bacteria to stick to eliminates the formation of the biofilm, which then in turn no bacteria and viruses or pathogens are able to survive.
Exactly. And this is the most important feature of AFM, is that we made the media 100% bioresistant, so we will fully prevent the formation of biofilm inside your filter. And how do we do this? Is with our activation process.
So we only select green and brown glass because through a very sophisticated process of sorting the colours. And the reason why we only want green and brown glass is because the metal oxides that give the glass that colour, chromium oxide, for example, in the green, and ferric oxide in the brown, this already has a natural bioresistance. So we're engineering the shape, and then through our activation process, we give that, increase the surface area of that glass, which increases the charge on that glass. And the way that it works is, as the water's passing through the filter over the surface of the glass, the surface charge acts as a catalyst and breaks apart the H2O, the water molecule, and releases these free radicals, these hydroxyl radicals. And that makes it impossible for any free-floating bacteria in the area to actually reach that surface. It's like a hot plate. You know, it just physically cannot reach the surface.
Cannot start to secrete the biofilm. And this is why if you see white glass on the market, you know that it cannot become bioresistant. It may be very clean and clear, you know, when you open it from the bag. But it will never prevent the formation of biofilm because you don't have these metal oxides.
At our plant in Edinburgh, we probably receive nearly 50% of clear glass that we consider a waste product. And we have to sort that out and send that off to other industries for making whiskey bottles or medicine bottles, for example. It's just the green and the brown glass that's the important colour.
Okay, so you got it, no biofilm again. We fully prevent it. No risk of pathogens, no problems with channeling, and no loss of efficiency. Stable, reliable filtration performance. And this is important when we talk about filtration efficiency. It's not on day one, it's constant.
We've got some examples later to show you.
Our number 2 subject of the day is and number 3 biggest problem of the biofilm is the formation of trichloramines. This is the very big problem linked to biofilm, is the formation of trichloramines.
So did you know, when we are submersed in nice warm water, we're excreting substances from various orifices from the body? Usually in the form of urine, sweat. Even an Olympic swimmer can excrete quite a significant amount of these substances.
Yeah, that's a lot. 1 liter in 2 hours of swimming. Yeah, that's a lot, quite some amount. Yeah, and this sweat and urine is composed mostly by urea, which is an organic compound, and that will feed all bacteria in the biofilm.
It's the perfect nutrient for bacteria that's thriving in the system. Yeah.
So the bacteria they eat this urea. And when they eat it, what happens?
They poop out ammonia.
Ammonia, yeah. And ammonia is inorganic.
Yeah.
So from urea, which is organic, to ammonia, inorganic. And when ammonia reacts with chlorine, we form these inorganic chloramines.
Yeah, these are the combined chlorines.
So combined chlorine. So mono, di, and trichloramines. And the trichloramines are the famous volatile ones that gas out.
Yeah, these are the ones that really, through agitation of the water, it gets released into the aerosol. And it's the one that really smells of chlorine. It can irritate the eyes, nose, and throat. And the unbeknowing bather just thinks that there's too much chlorine in the water. Yeah. But in fact, it's too much chlorine byproduct that's existing in the water. And it's a sign of quite an unhealthy bathing environment, in fact. Yeah.
No, if you have a smell. And also, according to the pH, you will form mono, di, or trichloramines. And the biofilm is very acidic. Yes. Usually you form these trichloramines at the pH below 5. And in this biofilm, very acidic, you will mostly form these trichloramines. So very, very bad for the throat, the lungs.
Respiratory tracts,
They inhale at the surface of the water, as you see here, by the bathers. Also the...
right where we're swimming,
The staff, of course. And they will really damage the protective layers of your lungs. And we have this official disease, lifeguard lung disease.
Lifeguard lung, yeah. I mean, there's instances of people that have gone on later on in life to develop asthma with no family history, and they can trace it back to the time that they spent in their youth, or maybe whilst they're at uni, earning a few quid as a lifeguard, spending that hours and hours on poolside, breathing in these toxins.
Yeah, when they're volatile, they are toxic. If they stay in the water, it's less of a problem. And this is again the promise of AFM, is that we don't have this biological conversion of urea to ammonia. So urea will stay urea in the water, and you don't have the formation of ammonia, and then you don't form these inorganic chloramines and trichloramines. So the promise is really 2 to 5 times less inorganic chloramines and trichloramines compared to sand.
Compared to sand, yeah.
So very much cleaner hair, healthy hair, and this is how it works. Another byproduct, which is also volatile and toxic, that we talk a lot less than trichloramines, is the chloroform.
Chloroform, trihallomethanes, yeah.
Yeah. So how is it formed, Jimmy?
Well, this is where you get, this is the process of oxidation. It's when you've got a long-chained organic molecule, organic compound, and it can be with chlorine or even UV, basically chopping up this long-chain molecule into smaller molecules in the form of a methane.
Yeah, that's the smallest organic molecule you have is the methane, yeah.
So it's a partial oxidation, and that methane then reacts with the chlorine again in the water, and you get an atom exchange in this case.
Yeah.
Hydrogen exchange for a chlorine to form a chloromethane, then you get a second exchange to dichloromethane, and then, what comes next? Trichloromethane, and again, this is the volatile one, the unstable one.
So it's a methane with 3 halogen atoms, and this is why it's called trihalomethane.
Trihalomethane, yeah.
And what do you need? So to form this chloroform and THMs, you need 2 things. You need chlorine and you need organics. So less organics means less potential to form THMs, and less chlorine also. If you reduce the chlorine demand, you will have less potential to form these THMs. And this you can confirm with 2 parameters actually. The one is the TOC, total organic carbon. This is really an indicator of your organic pollution. And you also have the KMNO4 consumption that you can control. And if these 2 parameters are high, you cannot have low THMs. It goes together.
Yeah.
They are linked together. So to form THMs, you need chlorine, you need organics, and you can control this organic pollution like this. Good. I said even more harmful than trichloramines. Why? Because not only it goes through your lungs, but also passes through your lungs to reach your bloodstream.
Yeah, again, the water is agitated, it's released into the aerosol. It's an odorless gas. It's very difficult to monitor and to measure in the air. You wouldn't really know it was there, but particularly sensitive to underdeveloped lungs in babies, pregnant women. And this is why AFM is such a popular choice for baby swim schools.
Yeah, exactly.
They recognise the benefits that it brings.
And below 2 years old, also the blood-brain barrier is not fully developed. This barrier that protects the brain from the pollutants. These babies, so that can be really harmful. So this is why we, with AFM, we have a very good solution to reduce this chloroform formation. And how do we do this? Is by filtering a lot more organics from the water. So you remember we had this AFM standard. We still have the standard, which is negatively charged, hydrophilic. And on the bottom, you see the AFM-NG, which is hydrophobic.
It's frightened of water. You see the water get repelled in that movie, whereas with the standard at the top, the water just gets absorbed.
Yeah. What does it absorb a lot more efficiently?
Other hydrophobic materials, such as organic matter, proteins, organics, oils, lipids. And you know, one of the reasons why Howard developed this particular type of AFM was to filter out microplastics from wastewater.
Originally it was developed for this,
Plastics are hydrophobic.
Then we realized it was also better for pools.
Perfect for pools.
Yeah. So you can remove more organics from the water, and therefore you have less potential to form chloroform. So we filter about 50% more organics than sand, and therefore we will reduce up to 50% the formation of chloroform, THMs. Like I said, another thing to reduce this chloroform is to improve the filtration efficiency. And these filtration test results are not from us, it's from the IFTS.
Yeah, it's not us telling you how good the media is. This is independent analysis carried out in the IFTS laboratory in France.
Yes, where they test, so you see here the different media. So it's always fresh media, without biofilm.
No flocculation, no coagulation.
The filter, the tests are performed at 20 meters per hour.
So typical commercial pool filtration velocities.
And on the bottom, you see the size of the particles, and on the left, the removal efficiency in percentage. You see that with AFM-NG, we can remove 95% of all the particles down to 1 micron. So this is really, really good. And what came as the second best?
Well, this sand product that came in second best at 20 microns was actually a sand product from a pit in the UK, Lake Buzzard pit, which has since been closed down because it's been depleted. Yeah. Another example as to why we should move away from sand, because it's not environmentally friendly, it's not sustainable, it's destroying habitats.
Yeah, coastlines, rivers, and all. Yeah. And it's forbidden in many countries to extract sand.
Okay. Yeah.
There's even sand mafia in Morocco and India.
Sand mafia.
Yeah.
Okay. I get it.
So in this case, it was not glass media that performed after AFM the best.
It was sand. Yeah. Then we have a glass material coming next, I think.
95% of all the particles down to 20 micron, and the best glass after that was this one. EGFM 25 micron filtration performance. Yeah, again, fresh media. We know that the sand after 6 months will not show the same performance. It's more like 30, 40 microns.
But worlds apart, absolutely worlds apart from the performance of AFM.
Yeah, and this is the charge. This is the increased surface area, the shape, activation, shape. Yeah. So to summarize for the chloroform is. We have this 1 micron filtration performance, so we can reduce the chlorine demand thanks to this, but also this hydrophobic surface will remove 50% more organics. So not only we have 50% less THMs, but also lower chlorine consumption and also the turbidity.
Well, I think this is the first thing that people really notice when they make the switch from sand to AFM is just how clear the water is. In fact, they sometimes say, I can now see the imperfections of the pool finish down at the deep end. You know, didn't know how to crack tile down there at the deep end before because the water's so crystal clear.
Yeah, and this is really the 1 micron filtration that makes the difference. So very low turbidity, up to 50% less THMs, and reduce chlorine consumption by approximately 30%. You will tell me why only 30%? It's because most of the chlorine demand comes from these dissolved pollutants in the water. So really, if you want to increase or decrease the consumption, the chlorine demand, you have to use flocculation and coagulation to remove these dissolved pollutants, precipitate them, and then filter them with AFM. And this is what we do with our APF,
all polyfloc.
So AFM combined with APF, we go down to this 0.1 micron filtration performance. And the best filtration, the lowest the chlorine demand. And in this case, we can reduce it by 50 to 80%. So this is a lot more efficient.
You know, we can also remove nutrients like phosphate using APF as well.
Phosphate, yeah.
Phosphate is a great nutrient for bacteria and algae as well. So again, stopping any problems at the source.
Yeah. So less chlorine, less potential again to form these THMs. Okay. Number 3.
Total combined chlorine.
Total combined chlorine.
So what are we measuring when we talk about total combined chlorine? We're actually measuring organic and inorganic chloramines. Now, whether you're using DPD number 3 into your DPD1 that shows your total chlorine, which you then deduct from your DPD1, or you can go straight to DPD number 4, which gives you total chlorine, and then you subtract your DPD1. That is the sum of your total combined chlorine.
Yeah. And often people ask us, will AFM reduce the total combined chlorine?
We don't give that promise.
We don't give that promise. It's because, as we said, we reduce strongly the inorganic chloramines, but not the organic chloramines. And it's the opposite as sand. In the sand system, the total combined chlorine will consist of a majority of 90% of inorganic chloramines and only a small part of organic chloramines. Mm-hmm. With AFM, it's the
opposite.
It's the opposite. Because urea is not converted to ammonia in the filter, so urea stays urea and also reacts with chlorine to form organic chloramines. Organic chloramines are a lot less harmful. They stay in the water, they build up very slowly. They pose zero harm for the health, but they don't make the difference when they control combined chlorine.
When we do the test, yeah.
So it's very important for the next subjects and solutions for combined chlorine is to understand that with a AFM system, your combined chlorine is consists of 80-90% of organic chloramines and only a small amount.
Small amount of inorganics, yeah.
Good. So what are the solutions? So, because in many countries, there's not much to do because these limits are very high. You know, in France, it's 0.6 ppm for combined chlorine.
Hey, well, that's pretty good. You know, in the UK at the moment, our standards stay, you can have a maximum combined chlorine of half that of the free chlorine.
Okay,
with
so
a maximum
get high, yeah.
With a maximum of 1.
Yeah.
You know, compared to Switzerland, for example, where we are today, Flo.
Yeah, 1 is a lot, yeah.
0.2.
0.2, yeah, and therefore...
And this is a regulation, not a standard, not a recommendation. This is a regulation. You know, pools can actually be closed down
if you're not below this.
If you're not below this 0.2 total combined chlorine.
And that become a bit more challenging. Yeah. Yes. So what are the solutions? Because we have solutions to get below the 0.2 ppm. Let's talk quickly about outdoor pools. In outdoor pools, we don't have, it's quite easy to get the job done with combined chlorine because of this big sun you see on the screen here.
This big UV lamp, yeah?
It's like a big UV lamp, yeah. So in this case, it always creates oxidation reactions in the water. With a properly sized DAISY system, AFM, some coagulation, flocculation, and ACO.
ACO, of course, on an outdoor pool instead of using something like cyanuric acid. ACO is...
reducing also the chlorine demand, less chlorine, less combined chlorine, but we get very good results below 0.2, doing not much, just a DAISY system, nothing else, and you get the job done. When it gets a bit more difficult is in indoor pools.
Indoor pools where we don't have that luxury of the UV from the sun, yeah?
Exactly, yeah. So in this case, you will see that with a DAISY system, you will be in general around 0.3, 0.4 ppm if it's well dimensioned, but it's not enough to be below the 0.2. So what else do we have to do? We have 3 options we will discuss today. Option 1 is actually the easiest, safest, best, cheapest, yeah.
Messiest.
And it's only about using some activated carbon. So You just have to replace 5-10 centimeters of your AFM. You will remove this, you replace it with 5-10 centimeters of activated carbon, and you will get, you will remove with this adsorption the combined chlorine THMs.
Yeah.
Does a very good job. Nothing else. I mean, it's quite easy.
You will lose a little bit of chlorine as it passes through that thin layer of active chlorine, and when you have, activated carbon, and you will need to do rinsing after a backwash as well, because you will get some fines from the active carbon coming back through. And it will also need to be topped up and replaced on an annual basis as well.
It has a quite high bed expansion, so you have to make sure you have enough...
the freeboard on the filter, yeah.
Another important point is to use activated carbon made from coconut shell.
Yes.
Because you'll see it's often mixed with this anthracite H and N. We just don't have we will talk about it in the next slide. They'll have the same properties. And why only 5 to 10 centimeters of activated carbon?
Yeah, well, like I said, if we will lose a small amount of chlorine through that thin layer, but if we go any more, we will probably lose a lot more chlorine, and then we're running the risk of biofouling occurring within the activated carbon itself. So we can start to get the same problems that we get with sand.
After this 30 centimeters, you will completely your chlorine is gone. You don't have this catalytic reaction, free radicals, and you get this biofilm at the bottom part of your activated carbon. Mm-hmm. So never more than 5-10 centimeters. You will see that you also will expand or extend your backwash frequency thanks to this layer.
Yes, yeah.
So quite a good solution in a way. You will consume some chlorine. There is some rinsing to do, which you don't have to do with AFM. Very good solution. And again, use activated carbon and not anthracite, because anthracite doesn't have the same properties and has a surface 3 times smaller than activated carbon. So you need to use 3 times more. So for the same results, instead of 10 centimeters, you need 30 centimeters. And also it can contain iron, which you don't have with the coconut shell activated carbon.
We have had some instances, again, back in the UK, where the installers used anthracite H, and after a few days, the pool has appeared with a very slight green tinge because of the level of iron contained in this.
So go for coconut. This is used a lot in Germany. They make it work somehow, but really activated carbon, much better solution. Anthracite N, don't use it. It's not thermically activated. 0 absorption capacity, so don't use it for pools. It's not the solution. Okay. Another way to use activated carbon.
Yeah, this is quite a neat way of using activated carbon on a side stream basis. I think it's quite popular in some Scandinavian countries, where you just take 5 to 10% of the total flow on a bypass through a separate carbon filter. Beauty of this, of course, is you can control open or close the flow depending on the level of combined chlorine in the system. I was saying,
stop it.
The downside to it, of course, though, is whilst there's no flow, and because it's only carbon within that filter, it will become prone to biofouling in time.
Also,
but another
5-10% of your total flow rate, and also make sure to have the proper diameter for your filter.
Yes, filtering velocity of about 10 meters an hour.
Good. We covered activated carbon. That was the goal.
That was the goal.
Option number 2, a very famous solution, right, Jimmy? You see it a lot in the UK. It's used in most of the European countries, right?
Yeah, medium pressure UV is recommended pretty much in public pools, commercial pools in the UK. It's very common. It's very effective, I would say. You do, again, lose a little bit of chlorine through the system. It's there really for 2 reasons. First of all, it takes out the combined chlorine. But secondly, it acts as a belt and braces against Cryptosporidia, for example.
If the lamps or the water is clear. No?
Yes. But we're just on the subject of Cryptosporidia. We're talking about these succus that are about the size of 3 to 6 micron. Well, if you are using sand filtration, we know it's only filtering to 20 microns, so that these cryptosporidia will soon pass through the filter.
Yeah.
But if you've got a full flow UV in place, then it will get destroyed.
Yeah, because they're resistant to chlorine, but
UV will chop it up.
Yeah.
But if you're using AFM filtering to 1 micron, already we create a barrier against cryptosporidia.
Yeah, and if you really want to be 100% sure with coagulation, flocculation, you're sure to remove them.
Even more. The other downside of medium pressure UV is it's not a complete oxidation process, it's a partial oxidation, coming back to the oxidation of the long-chained organic molecules.
Yeah.
You know, into
You're forming methane.
You're creating more THMs,
Yeah, you're catalyzing.
They're energy hungry,
Yeah.
so they consume a lot of power. They're very expensive to invest in, and they need regular maintenance as well.
The flow rate, there are usually big systems. Consumption is high, and the heat creating the scaling, and you have to.
Which we need the wiper systems to keep the tubes clean as well, so it's emitting a constant light.
So let's say it's a good solution for combined chlorine, but not our favorite option.
It's not our preferred
and especially
option,
because of this THM. Yeah. And this was confirmed actually with a case study we will show.
We will show you. Yeah.
Last point regarding medium pressure UV. When it's oxidizing these monodi and trichloramine, it also forms nitrate.
Again, which is a nutrient for algae and bacteria. Yeah, you see on that graph there that the wavelength that's emitted from medium pressures over a broad spectrum of light, which is why I think it's so energy hungry. But you can see it's very effective there at taking out the inorganic chloramines that we're not producing with an AFM system.
So again, not very good, a bit like phosphate. We don't want nitrates, we don't want these THMs. And this was confirmed, like I said, in this case study. So this was also a very interesting case study made in Holland, public pool, 850 cubic meters, lots of bathers. We had 5,500 visitors per week. So
busy pool,
Busy pool, 1 filter, 2 pumps, 1 for filtration, 2 pumps for backwashing. So they had good filtration speed, good backwash speed. And they run this test, so that was an independent lab, called
analysis,
And they did that over 19 months. So once a month, always the same day, same time, to always have the same conditions, consistent test. And we did a comparison test, so in 4 stages.
So the first stage there, or stage 0 if you like, 2 months before any changes were made, was just running with the traditional sand filtration that they'd always run with. And then stage 2, for 7 months, it was swapped in for AFM and APF for coagulation, flocculation. And then they switched on a UV low pressure, in this case, a UV low pressure lamp for 4 months. And then they switched that off and replaced a little bit of the AFM layering with some active carbon. And the analysis that they did, I mean, these are all the parameters that they tested. I wouldn't even begin to try and pronounce some of the.
Me neither, especially.
So pretty comprehensive.
And there was over 40 different parameters. So quite complete testing. And certified. And what are the results we got? So here we focus on turbidity, combined chlorine, THMs, trichloramines, also the water consumption per bathers. What we see first is the turbidity. Just with AFM, APF, you get to the lowest possible turbidity. We had 0.1 NTU, really good. You don't have to do anything else.
And this
was not improved with UV or activated carbon. The second one is the THMs we just talked about, reduced by 50% with AFM and APF. And what you see here, very interesting, is with UV, back up 50% to 45 micrograms per liter. And when we stopped it, back down.
Back down with the activated carbon,
Combined chlorine, we went from 0.61 ppm to 0.4. So this is what I said, with a DAISY system, you don't get below 0.2. But in this case, we were at 0.4. Improved with UV to 0.3, and the best results were obtained by
the activated carbon. But the exchange on the reduction in the combined chlorine with the UV is that increase in THMs.
Yes.
Yeah.
Trichloramines, minus 60% with AFM APF.
Trichloramines in the air again. Yeah.
And the water consumption.
The water consumption is extraordinary. Yeah. Yeah. Absolutely fantastic results there.
So they had really perfect water quality using about 15 liters per beater instead of 45 liters. So really good savings, very fast return on investment. Yeah, very good case studies.
Mm-hmm.
And the last option, number 3, third option, is our advanced oxidation.
This is the Dryden solution, and a little bit more sophisticated than using activated carbon.
Yeah, a bit more sophisticated.
Yeah.
It actually comes from the drinking water, wastewater industry, and we decided, yeah, it's working very well. Let's use it for pools, let's test it, and the results are, you'll see, very good, very good. So what is advanced oxidation, Jim?
So Advanox is utilizing UV technology, this time low pressure, but a very high dose, as you can see there, 5,000 joules per square meter.
Yeah, that's
UV
about 50 times more than what they use in drinking water application.
Yeah, so pretty strong. But what we're doing here is we're bringing in hydrogen peroxide on the incoming side of the UV chamber.
Yeah.
And with that high dose of UV radiation, this breaks the hydrogen peroxide molecule.
Yeah.
Splits that molecule, releases hydroxyl radicals, got exceptionally high oxidation potential, and that gives you a complete oxidation of any organics that are existing in the system.
Yeah. No, that's a complete oxidation.
There's no byproduct.
So we don't use UV to disinfect the water. We use it to form these
hydroxyl
radicals.
Yeah. There's no increase in THMs. There's no byproduct to that
complete
process.
Oxidation. No byproducts. And the beauty also is that we can go, like we said, we will use this advanced oxidation with a DAISY system. With the DAISY, remember your combined chlorine consists of a majority of organic chloramines, which build up very slowly in your pool, and that's how we can use Advanox the way we do. So we only need to go through the Advanox system every 2 to 3 days. So you take your total pool volume, you divide it by 60, 2.5 days, and you get to that gets you the flow rate
through the bypass. Yeah. And you wouldn't use Advanox with sand filtration because of the inorganics that we've got present. Yeah, it won't work. It only be used with a AFM.
Inorganic, they form very quickly. They gas out. We talked about it. So only with the DAISY system with an AFM filter, and this way you will, from one side, reduce the inorganic, and the other side the organic chloramines. To have a total combined chlorine below 0.2.
So because it's utilizing low pressure UV, it doesn't have that energy that energy appetite that medium pressure does.
Yeah,
so
5
the
to 10
operation
times lower consumption.
Are much lower, yeah. And because of the complete oxidation of the organic matter, no
THMs. And these are the test results in this pool in Brighton Bar.
Yeah, just down the road here. Yeah, so they were operating free chlorine at 0.4. That would be something else, I can tell you, in the UK to be able to reach free chlorines that low. But their combined chlorine, their total combined chlorine again was still above that of the allowed and permissible limit of 0.2. They were operating at 0.34. So after the DAISY and Advanox was put in, you can see that's dropped right down now to 0.0.
Yeah, so then stable, never above 0.2.
Quite extraordinary.
Average of 0.09 even, so yeah, very good. Yeah, so again, always in combination with DAISY, I mentioned it. Not only you will get the total combined chlorine below 0.2, but also you get really pure, healthy water. So.
And it's not just taking out these organics, it will take out substances that you wouldn't even know that were there, like cosmetics, pharmaceuticals, toxins, So it's
really
be all right when you say pure water,
Low energy, long lifetime, and really the combination for the best results. Good. Let's move to the important subject, how to make savings, water savings.
Water savings, This is analysis from Matthew Dryden, son of Howard, up there in sunny Edinburgh. This is Matthew's wet lab.
We invested quite some money in this wet lab, really sophisticated wet lab with these columns you see here where we can compare side by side all the media, same conditions. I'll let you take...
what Matthew's done here is pretty much replicated what they do at the IFTS lab in France. And this keeps Matthew very busy and very happy, I must add as well. He does enjoy doing these tests. So, as Flo says, we can do an analysis on our own media and other media side by side to see how it behaves in comparison. The conditions of the water is the same for all of the tests that we do. And we use this recognized ISO standard test dust as a contaminant called Arizona test dust.
We have particle counter on the incoming water
and on the outgoing. And because the water's so soft up there in Scotland, not only does it make very good whiskey, it also means that we can remineralize that water to replicate it from anywhere in the world. If any of our customers
can get it to the right level, and
and we can do analysis to replicate it in our customers' countries, which is quite neat.
So here again, we use it a lot for filtration performance, but today we want to focus on
the all-important backwash. Or as I like to call it, the emptying of the bin. Because it's all very well having a good filter media to capture particles, but you've got to get that rubbish out of the bin.
You can have the best filtration in the world. If your trash is staying inside your filter, you will not get the results and the water quality you expect.
So for a efficient backwash, you need a flow velocity high enough to fluidize the bed and expand it by at least 15%, preferably 20%. To allow all the trapped particles deep down into the media to get flow out and out of the filter vessel itself. So we can see the analysis here, the results that Matthew's taken with the backwash flow velocity along the bottom axis and the bed expansion along the left-hand axis. The AFM will fluidize to 20% with a low velocity of only 30 meters an hour.
Very good, In some cases, we don't have the high backwash velocities, and with AFM, in some cases where you don't have the speed, and 30, usually you have the 30, and therefore you get the expansion with AFM at only 30, which is really good and safe. How do you say?
Well, that's typical of the UK when we've got a standard that says that the backwash velocity should be a minimum of 30 meters an hour. In most cases, the system has been designed to that 30, so we are, in a lot of instances, limited to 30 meters an hour. And you can see in the...
same in France, they filter at 30 and they backwash at the same speed. It's often the case. So many countries now, new installations, usually they calculate with a higher backwash in Europe, but
that can only be a good thing, because you can see on the results graph there that the next best performing media, again, compared to AFM, was this sand from Germany that needed
a bit more than 40.
Just 42. A little over 40 meters an hour to get that 20% bed expansion.
Dutch sand, 58.
Up to,
And then the other glass media, really, you need more than 65.
You need huge velocities, And a lot of this is down to the shape and size of the granules of this glass. A lot of them are very slate-like, very flat. And Matthew found that when they went into backwash, they lift and then flip and just drop straight back down again.
So all the water, the particle, the bed expansion, the bed is not being expanded. So very good expansion, the lower velocity, and you see that again, sand performs better than other glass media for backwash, not only filtration but backwash, and some media you cannot backwash.
Just simply cannot empty the bin. You'll never empty the bin. And after a period of time, it's going to block up and you'll need to replace that media.
We did another test, very interesting. That's one of my favorite one, where we measure the turbidity on the backwash line.
So this is measured in NTU, right? And this is how cloudy the discharge water is.
And so you have the duration, the backwash duration on the bottom, turbidity, NTU. And we see that we perform a backwash at 30 meters, like you said. So AFM, what do you see with AFM? Very high peak.
It peaks very, very quickly, doesn't it? With very turbid water, and then it drops off just as quickly. And then when the velocity is doubled to 60 meters an hour, we got a flat line compared to the two sand products that have got a similar peak, albeit over an elongated period of time. But just look what happens when Matthew increased the speed to 60 meters an hour. We actually got a secondary release of debris from the filter. So it tells us at that lower speed, we haven't fully emptied the bin.
Yeah. So the sand were not fully backwashed at 30 meters.
So when we're backwashing by sight glass and it runs clear, this doesn't mean that that filter is clean.
Yeah, exactly. Yeah.
If there's been instances again where installations backwash with a single pump, and then you ask them to do the same backwash but put on the second pump, double the speed, and they see a second release of cloudy water coming out through the sight glass.
So this is with sand. You see sand 0.4, 0.8, 0.5 to 1. And the results were amazing when we compared the AFM to other glass.
The other glass media.
So same test, first backwash at 30 meters. We have decided peak of turbidity, no second peak at 60. And look at what happens with all the glass.
This was the clear plate glass, the virgin glass or window glass as it's sometimes described. So we got a half decent peak on the lower speed, but just look how much more debris came out on the higher speed.
Yeah, so it was not backwashed properly.
And the crushed container glass, well, we didn't get much out at the low speed, and we didn't get much more out at that
Well, that
higher
means
speed.
that you need more than 60 too.
Yes. Well, if you think back, the bed expansion graph, we were up to 70, 80 meters an hour in some instances. So, systems will not be designed to deal with that flow of water. So you just simply cannot backwash these medias properly. Cannot.
Very interesting test, yeah. This is another test that we did. Now we want to measure in how long, when is my filter clean. So we want this turbidity peak, but we want to calculate in how much time I reduce this turbidity by 90%. 90%, my filter is clean again. I can go back to filtration, and we measure this time, less water consumed.
Well, the backwash duration is directly proportional to the water consumption, yeah.
So with AFM, we have this peak, and after 60 seconds, we went back to this 90% removal.
The turbidity had dropped right back down within that time. And the sand, both sands in fact.
So here we test at 60 meters because we saw at 30, they are not fully backwashed.
Yeah.
So let's take all the media at 60 to have some kind of good
comparison. Yeah. So AFM, 60 seconds, and then both the sands were pretty much double that of AFM. And that's what we find in the field as well. When people have made the swap to AFM from sand, we're typically reducing their backwash period by about 50%.
Yeah. So again, that was sand, and now with glass, even longer.
Even longer, yeah. That's the clear plate glass, 130 seconds, and then the container glass, which was 140 seconds. But again, this is at 60 meters an hour. And we know that it's not fluidizing at that velocity, so we haven't really emptied the bin.
So much more water, but also we know that the filter bed is still polluted.
Yeah.
Okay, and this is the result. So this is really the consumption, the water consumption per square meter of filter surface. You get at 30 meters on the left and 60 meters on the right of the screen. But again, these results, this water consumption at 30 meters, they don't mean much because they are not backwashed properly. So if you look at the 60 meters, you see that with AFM, we will consume per square meter of filter surface 1,730 liters. And that's how we don't have in percentage, the comparison.
No, this is just a calculation that Matthew's done, as you say, per metre squared of surface area. The reality is at 30 metres an hour, particularly in countries where we're restricted to that. It's all relative, isn't it, depending on the media that's being used. Because AFM fluidizes so readily, so easily, we evacuate all the debris over a very short period of time. So therefore, we use a lot less water. But what's really interesting, and it took me a little while to get my head around, is if we double the speed, naturally you think you're going to use more water, but because it's over a shorter period of time, we actually save even more water. So our message here is if we can backwash and have the system sized for a higher velocity, we actually save even more water.
Yeah, you see 60 meters, and this is about 30% less at 60 meters than 30 meters. So short and fast to make water savings is the right way to go. Yeah. Good.
Yeah, so this is our conclusion. Unless anybody else can prove otherwise, through independent analysis, AFM is the most efficient media for fine particle filtration, as demonstrated by IFTS. But more importantly, you know, is that backwash. We can't emphasize enough just how important backwashing is. And we believe that AFM is the best backwash efficiency, bed expansion, retain soils removal, and backwash time and water savings.
Yeah.
It provides the long-term stable filtration performance. And I would say, as I do on the bottom line of that previous slide, you know, at 30 meters an hour, and I say that because that's where we're at in the UK, other filter media is just not fit for purpose. And do you know where I got that phrase from?
No.
You know, if anybody ever says to you, "You've sold me a product here that's not fit for purpose," you know they've been speaking to a solicitor, because I'm married to one.
Good, yeah. So very good in, not only filtration, but backwash efficiency. I would just wanted to make a quick reminder on this commissioning, because
very important.
also like activated carbon is hydrophobic, but AFM engine is hydrophobic. And when you first put it inside the filter, you should let it soak, let it wet, or go directly into filtration. And you can do so because it's a very, very clean filter media.
You'll see in this movie here just how clean it is, and see how the AFM
First
is rising because it's hydrophobic nature. But you will see just how clean it is. Now, if you were to put the filter directly into backwash, you're probably going to lose a fair bit of that media. So
because it's hydrophobic, you cannot backwash it right away. You might lose.
The angel share, I think Dominic likes to call it. But see how clean it is. So you can, as Flo says, put it directly into filtration mode. There's going to be very little fines come through what is essentially a closed system anyway. Or if you're a little bit wary, you can just put it into a rinse mode, to wet it.
Another point about this hydrophobicity and this air backwash, some pools are using air backwashing, which is used with sand because of this biofouling again.
To break up the biofouling of sand, to scrub the sand.
And this problem we don't get with AFM. So first of all, you don't need to backwash AFM with air.
No air scouring required.
The best results will be with pure water backwash. But if you are forced or you have to use air backwash or they require this, you know you cannot use the AFM because it's hydrophobic again. If it gets again in contact with water, you have this problem.
It floats again.
Again, mixing a bit the bed. And so if you have this air backwash, always use the previous generation of our standard AFMS, negatively charged, and this one can be backwash with air. Yeah. So AFMS, air and water okay, NG, water only. Last point, our AFM DIN grade.
Introducing DIN grade.
So why 0.7 to 1.2 millimeters is because of the DIN norm. Like I said, in Germany, you want the DIN requirements you have to meet these requirements and you need this exact grain size. So we made the AFM DIN 0.7 to 1.2. And we used it in Germany and we realized it had some advantages compared to our traditional grade 1.
In certain applications, with a much higher loading capacity.
Yeah, so number one is the holding capacity. You know, when we say we want to backwash the filter, usually you have this clean filter bed, the pressure, and then once this pressure rises up to 500 millibars, 0.5 bar, you want to launch your backwash. And this happens with AFM grade 1 and G after, collecting 2.7 kilo.
2.7 kilo per square meter.
And with AFM, the DIN grade, you can hold a lot more than twice more, to 6 kilos before reaching this plus 500 millibar.
So you can extend your runtime between backwashing.
Yeah. Instead of having to backwash, let's say every 2 to 3 days, you can backwash every 7 days with AFM DIN grade.
So outdoor pools, for example, with a high organic bather load, or over subscribed public pools.
You have some pools always complaining I have to backwash too often. So this is really a good solution, is to extend this backwash frequency.
And it filters pretty well too.
Very well. I mean, it's not the 1 micron of AFM grade 1. We filter them to 4 micron. So this is really good. Considering the grain size, 0.7 to 1.2, this is really good. And if you compare it to the sand, the DIN sand, same size, 0.7 to 1.2, you had more than 30 microns in the filtration. So So again, a world between the two. So twice more holding capacity, very good filtration down to 4 microns.
Oh, I sense a but.
There's a but, yeah.
There is a but.
There's a but, and yeah, the DIN grade has to be backwashed more than at 30 meters. We saw with the grade 1. You need minimum 50 meters per hour to backwash the DIN grade. You see here the bed expansion. We want this 15-20% bed expansion, and we get this at around 50 meters per hour.
And this is just because it's a larger grain size, right?
Yeah. Yeah. Okay. So very good. Another advantage is that it's one grade only, we call it. If you have nozzle plate in your filter, you can use 100% of DIN grade. If you have laterals, you need this grade 3 to cover the laterals, and you can use 75% of the DIN grade. But really practical. So more holding capacity, very practical, 4 micron filtration, but you need
the 50 meters an hour backwash.
Yeah, 50 meters. Available in 25 kilo and 1 ton bags. This I've said it.
Okay.
Good. Summary?
Summary, yes.
Let's close it up.
So with AFM, Daisy, we're eliminating that substrate for bacteria growth, no biofilm, which in turn means no disinfection byproducts. We get a consistent and stable, reliable filtration performance.
Yeah, when we say 1 micron, it's 1 micron for a long time, and you will see it in your case too.
Yeah, yeah.
Better filtration means we remove a lot more organic substances. We have less THMs formed. So we filter down to 1 micron, and we remove more organics.
We've got a more efficient backwash, even at slower velocities of 30 meters an hour for emptying the bin. And because of its bioresistance, we don't require air scouring, so a saving straight away. You can turn the air
scourer blowers, and save energy. And we can save up to 80% backwash water compared to sand, and especially other glass media. And if you are doing air backwash, again,
if it's a must, please use our standard grade, not the NG.
Yeah. Perfect. Good summary.
So one question I get asked. So, how long does AFM last?
Yeah.
Well, it was only earlier this year I took the opportunity to visit Ian here at the Leisuredrome, which is just outside of Glasgow, a place called Bishop's Briggs, where AFM was installed 20 years ago. And the water quality today is as good today as it was 20 years ago.
Perfect.
Yeah, so a very, very happy customer that's been enjoying multiple savings over the last 2 decades.
That's always good to hear that and to get the manager as reports. Yeah.
Yeah.
So you can find this case study on our website too.
Yeah, that's just showing the turbidity of the incoming water there at 0.24 NTU, and the pool I measured at 0.27. So very similar to the tap water, top-up water. Yeah. Another instance was a pool in London that had been fitted with a very sophisticated anti-drowning device. Unfortunately, it kept triggering false alarms due to the poor turbidity of the water again. So the service company recommended AFM. They took their advice, and it solved the problem overnight.
So turbidity, like we saw, it's...
Yeah, absolutely gin clear water, so no more false alarms. So they're looking at rolling that out to the other sites where they have this system installed. And I love it when I get a WhatsApp message come through from installers, which you'll see on the next slide.
Next slide?
Yeah. This was a private school close to where I live. Yeah, this is what the message said along with these 2 pictures. Hey, Jimmy, that AFM is good stuff. That wasn't his exact words.
You made it politically correct.
Yeah.
No, very nice to hear. Okay, I think we're good for this session 15. We hope you enjoyed it. Thanks for watching, and we will leave you now with our latest AFM video for commercial pools. Why using AFM? In 3 minutes, you will see why you should use AFM in your commercial pools.
Thank you for listening.
Thank you. See you next time.
Running a commercial pool involves more than just maintaining clean water. It's also about ensuring efficiency, sustainability, and cost savings. Introducing AFM Activated Filter Media by Dryden Aqua, the world's most advanced filter media designed to revolutionize pool maintenance. adapted to all sand filters without the need for investment in extra infrastructure. AFM is made from 100% recycled glass in state-of-the-art factories powered by self-generated solar energy. Our process uses 100% rainwater for washing, and every byproduct is recycled or repurposed, achieving zero waste manufacturing and setting a new standard in sustainable production. Through a unique 3-step chemical and thermal activation process, AFM becomes the only fully bioresistant filter media available, effectively preventing bacterial growth and biofilm formation inside your filters. This advanced technology keeps your pool safer by preventing channeling, unfiltered water, and harmful pathogens from entering the pool. By inhibiting biofilm growth, AFM also prevents the biological conversion of urea into ammonia, which is responsible for forming harmful trichloramines, the root cause of eye, skin, and lung irritation. This results in healthier air conditions for all pool users and staff. And there's more. Our activation process significantly increases the surface area of AFM and makes it hydrophobic, allowing it to filter much finer particles down to 1 micron and remove up to 50% more organic substances than sand and other filter media. This dramatically reduces water turbidity, lowers chlorine demand, and minimizes the formation of harmful THMs like chloroform, essential for protecting vulnerable swimmers such as pregnant women, babies, and children. But that's not all. One of AFM's most impressive features is its unmatched backwash performance. Unlike other filter media that struggle with clumping, biofouling, and poor bed expansion, AFM offers exceptional bed expansion during slower backwashes, and without biofilm buildup, it can efficiently clear over 95% of all trapped particles during shorter cycles as well. This efficient backwash process uses up to 80% less water than other filter media, saving thousands of litres each year. It's not just a win for your operating costs, it's a major win for the environment. And last but not least, AFM delivers outstanding value. With a lifespan of over 20 years, it far outlasts traditional sand filters, significantly reducing costs associated with replacements, maintenance, and disposal. Choosing AFM means more than just upgrading your filters. It's about investing in superior water quality, cleaner air, a healthier bathing environment, reduced costs, and a sustainable future. AFM by Dryden Aqua.